Hello everyone and welcome back to a brand new episode of Funtastic Academy. In today's episode, we're going to learn about another new sorting algorithm. But not just any algorithm. Instead of seeing how to sort a list of numbers, today we are going to learn about an entirely new way of structuring data in a computer and the advantages that come with it. That's right, we're going to learn about heaps and the heap sort. Before we come to heaps, let's first answer the quiz question from last episode. The quiz question was, what is a more efficient partition scheme for the quick sort as opposed to the Lomoto scheme? The answer is the Hoare partition scheme. The Hoare partition scheme was introduced in the first ever quicksort paper, and it's much faster, although more complicated to program. With that out of the way, today let's learn about heaps, how they work, why they're useful, and how they can use to sort. Thanks for that, Camera Ayush. Now it's me here, Computer Ayush, here to explain the heap sort algorithm. Now, heap sort is a very unique type of algorithm. That's because, unlike every other algorithm we've seen so far, like merge sort and quick sort, heap sort doesn't just shuffle around the elements in a list. Instead of a list, it uses a completely new paradigm of storing data, and that's the heap. The heap is a special data structure designed for one thing and one thing only, which is finding the maximum or the minimum element in a list as efficiently as possible. You can see how something like this would be very useful in sorting. So, what exactly is a heap? How is it structured? How can we construct them? And how can we use them in an algorithm? That's what we're going to discuss today. So, what is a heap? The heap is a way of arranging numbers so that the biggest number is always at the top. Here, 8 is the biggest number, also called the root of the heap. From this, we can see that every element has some amount of children, at most 2 children. 8 has the children 5 and 7, represented by these slashes, and each of those have even more children until we get to the end. There are two important factors that a heap must satisfy. The first is that it must be complete. I can't just remove a number like this here, because that would mean there would be a gap in the numbers at this level of the heap. There can't be any gaps in the heap. That's why it's called a complete tree. The second property a heap must satisfy is the max heap property. This states that every number is always bigger than its children. For example, here 7 is bigger than its children 4 and 6. That's why the number at the top is always the biggest. It's bigger than its children, and those children are bigger than their children, and so on until we get that this element is bigger than every other element in the list. Now, we can also have min heaps. There, what changes is that every element has to be smaller than everything below it. Therefore, the number at the top will be the smallest element. Mini heaps are good if you want to minimize something like time or money spent. But here for sorting, we tend to use a max heap. Now, how do we store heaps like this? The answer is simple. All we do is we read every number in normal reading order and we store them in a normal list. The reason why we can store a heap in a list this way is that every arrow we see in the heap can be internally identified as a pattern in this list. Because the heap is complete, we can always find a mathematical relationship between the parents and the children. For example, take the number 5. It's the second number in this list if we start from 1. We can find the parent of 5 by dividing 2 the index by 2 and rounding down. This gives us 1, and the parent of 5 is the first number. Similarly, we multiply 2 by 2 to get the child of 5, which is 3. To find the other child, we just add 1. We get the next number after 3, which is 2. So, to find the parent, we divide by 2 and round down. To find the children, we multiply by 2 and then maybe add 1. That's all there is to storing a heap. Now the question arises, how do we make a heap? How do we take a random list and make it so that it satisfies this heap property where the biggest number is at the start? The answer is by using the heapify algorithm. I've divided the entire heap sort algorithm into these two portions. Here we see the main heap sort portion, and these first two lines are labeled as building the max heap. These two lines effectively carry out the heapify algorithm. They make the heap out of the data. But as you can see, it calls this extra algorithm called fix heap. So let's understand what fix heap does before understanding how it can be used to manufacture a full heap. Fix heap takes two arguments. I, the position which we need to fix in the heap, and n, which is how big the heap is. What does it do with these two numbers? Fix heap's job is to make sure the heap property is correct at a given I. Let's say at a given I, we can consider the heap looking something like this, with this being our I. The fixed heap algorithm takes it for granted that both of I's children are the roots of completely working heaps. So we have working heaps here. All we need to figure out is how to shuffle the number at the top so that the top is working. Now, because of the heap property, we know that the top number must be the bigger numbers in all of this. So we need to find the biggest number to fix the heap. But because we know the left half and the right half are already fixed, we know that the biggest number in the two halves must be these two. So the biggest number in the whole portion must be one of these three. So to fix the heap property, all we need to do is find the biggest of these three and put it at the top. Simple, right? Wrong. Because if you want to put one of these numbers at the top, you need to put the top number back in its original place. You need to swap them around. And now you have a new number there, which might violate the heap property. So you have to fix heap down again in this half to make sure that the heap property always remains satisfied. Maybe you'll understand clearer if I show you the code behind fix heap. We set largest, a placeholder variable, to be equal to I. Then we calculate its left and right children using the formulas I mentioned earlier, 2i and 2i plus 1. These two if statements set largest to the biggest among I and its two children. If A left is bigger than A largest, largest is left. If A right is bigger than A largest, largest is right. You may also notice we have statements like if left is less than n. Why is that the case? Let's say I was equal to n, the last element in the heap. Well, then 2i would be beyond the end of the heap. So it would get something that isn't valid in this array. That's why we're using these comparisons to make sure that never ever happens. Anyway, after these comparisons, at this point in the code, largest will be equal to the largest element under I. If largest is equal to I, then problem solved. We knew the heap was fine all along. But if largest is not equal to I, then we have to put largest where I was. We swap their positions. And then we fix heap the new position of largest. We fix heap it so that we make sure that any violations are fully fixed. Now we can understand what these two lines which make the full heap do. N by 2 is the first element in the heap that's not a leaf. N is the last element. In this case, n equals 8, so 8 would be the last element. N by 2 is its parent, which is 3 over here. We go from n by 2 to 1, which means going through all the nodes in the heap which are parents. And for all of those nodes, we just run fix heap. Simple. Now let's do a quick demonstration on how heapify and fix heap make a max heap. Let's say we start with a list of numbers like this. These are 8 numbers in a completely random order. When we make a heap like this, as you can see, the heap property is very much violated. 4 is greater than 7, 7 is greater than 8, and all of that. So we need to fix every single parent, starting with the parent furthest down, which is this position, the position 3. We check its children, which in this case is only 5, but 5 is bigger than 3. Therefore, what we do is we swap their positions and we fix heap. In this case, 3 is already at the end, so when we swap them, there's no need to do any further down. The same thing happens with the next parent, 7. 7 is the first element before where 3 was. 7 is smaller than 8, so we swap 7 and 8, and that's it. Easy. But now, when we get to 1, we get some problems. 1 is smaller than 5, so we swap it in 5's place. 1 is also smaller than 2, but 5 is bigger. 5 is bigger than either 1 or 2. So we swap with 5 to make sure the heap property is satisfied. But then, the heap property is still broken because 1 is shown to be bigger than 3. The solution is that we fix heap at the new position of 1, which swaps 1 at 3 to give us this. So at this point, everything under 5 is a perfectly working heap, and everything under 8 is a perfectly working heap as well. Now all we have to do is solve for the root. The root 4 is smaller than 8, so it gets swapped in their position. It's also smaller than 7, so it gets swapped down once more. And now we have a fully working heap with the biggest number, 8, at the top. This is how heapify and fix heap work to construct a heap in the same list storage as we once had a list which was completely random. So let's recap what we just did. We learned what a heap is, why it's useful. We learned how to store heaps and the identities of finding a parent and a child in a list mapped to a heap. We then saw the fixed heap algorithm and a bit of the heap sort algorithm. And we saw how they can be used to fully construct a working max heap. In future episodes, we'll review what the remaining part of Heapsort does and analyze its time complexity to show why it's such a good sorting algorithm. Now, I'm going to pass the mic back to Ayush. Thanks for that, Ayush. Now let's recap what we learned today. We learned about what heaps are. Binary complete trees that follow the heap property. We learned how to store heaps in a standard list of numbers. And we learned how to create them from an unsorted list using the fixed heap and heapify algorithms. Next time, we'll get around to actually sorting with these heaps, as well as figure out what the time complexity of heapsort and heapify are. Until then, I will leave you with this simple quiz question. Who invented heapsort and in which year? Tell me the answer, and I'll see you on the next episode of the Funtastic Academy. Bye!